Welcome back, everyone. In this section, we're going to start talking about what is k-nearest neighbor, or KNN for short. In this lesson itself, we're going to give you or talk about the concepts that underpin k-nearest neighbor. So before we start off, I'm just going to copy some text that I prepare as descriptors to help you to understand what k-nearest neighbor is. It is both a classification as well as regression-based machine learning algorithm. So by then, I hope that you still remember from our earlier session on the different categories of machine learning that you recall this will fall under the supervised section. Okay, and a couple of characteristics of KNN works like this. It's first of all a lazy learner, meaning it is instance-based. Or another way of saying instance-based is that it's based on memory rather than learning the actual pattern or coming up with the function to describe the underlying data itself. So if you would recall, with linear regression, we will use y is equal to mx plus c as our function. If you're talking about something that's a little bit more complex, it could be a multivariate regression. It could also be penalized regression. They all have a specific function to go with it. Likewise with logistic regression as well. So for those machine learning model, they are what you will call learning from the actual function or learning a function itself. Now, the second feature of k-nearest neighbor is that it is non-parametric model. It is a non-parametric model. What that really means is that it's a distribution-free test because there is no assumption of the data needing to follow a specific distribution. Now, the common definition or specific requirement is that it needs to be normally distributed in some way, shape, or form. Now, typically when you're talking about parametric, it comes under the umbrella of probability distributions, where we use both descriptive as well as inferential statistics. The typical parameters that you would have come across would be such as mean, variance, and things like that. Okay, so when it comes to non-parametric statistics, it makes no assumptions about the probability distribution of the underlying variables itself. So that's really the key difference here. A couple of other examples of non-parametric model would be your decision tree as well as your random forest. Now, the more important part really is what is it used for? Now, at the end of the day, we're much more interested in the actual practical use of these machine learning algorithms. We're not just learning it for learning's sake. We want to know how we can actually use this machine learning to solve real-world problem. A couple of use cases that is used for would be predicting cancer, whether a cell is malignant or benign. In fact, we will do this as an exercise a little bit later. I will demonstrate that to you. Pattern recognition, so that's really similar to predicting, whether a cell is malignant or benign, purely from the pattern itself. A recommender system, these are all variant, except that the underlying core technology is the same, but is applied to, depending on where it's applied to. Other examples that KNN has been used quite commonly would be your computer vision, gene expression, and also protein to protein interaction, and 3D structure prediction. So essentially these are, as you start to see now, is that it actually start to be very pattern oriented, or rather it actually gravitates towards similarity of some sort. Now, what would be the disadvantages of using KNN? The one thing about it is that because it is memory based, right? It doesn't actually learn a function. It's very quick to train, but it's very slow when it actually starts being applied on big data. Now, it is very susceptible to the curse of dimensionality because of overfitting. The curse of dimensionality really describes the phenomenon where the feature space becomes too sparse for an increasing number of dimensions or fixed size training datasets. Intuitively, we can think of even the closest neighbors being too far away in a high dimension space to give a good estimate. Now this is really coming from Wikipedia, and there's a description of what KNN is. It helps you to actually understand why is it that it struggles in these settings. Last but not least, I always like to give you some references just to actually help you to, as a reference to learn from others as well, so that if you need to, or should you need to, you can actually refer to them. Now, just before we go, I just want to describe a little bit about the actual, what does the name K nearest neighbor actually means. K here is not specifically the name itself. K here in mathematics denotes a number. So it could be 1, it could be 2, it could be 3. So that's really what the K nearest neighbor actually means. So that's hopefully give you a sense of what we're trying to do here. And finally, in terms of the actual setting of the so-called pattern or learning, in a sense that K nearest neighbor will work, is these steps here. So let me just describe this. You probably won't actually appreciate what this really means until a bit later on in the next tutorial when we actually go into an example. Let me go through them. So the first thing is that you choose the number of neighbors. Okay, that's denotes by K. And then you decide on a distance matrix. Again, later on we'll talk about the different types of distance matrix that we're going to use. Find the number of nearest neighbors of the sample, and then assign the class label by majority vote. So that's really giving it a label accordingly. So with that, that's really a little bit of the backdrop, a little bit of the concepts and theory on K nearest neighbor. In the next session, we're going to go into applying it into our iris data sets, and I'll talk a little bit more about that. Hopefully through that practice session, you actually get to have a little bit deeper understanding of how K nearest neighbor works. So let's look at the next session, and for now, let's take a break. Thank you.